This conference will now be recorded.
When I was giving the presentation at an education conference back in June, but the content will stay pretty similar, and I'll probably skip a lot of slides. And this work, essentially, we are using a data-driven model for doing question generation. And the model that we use is essentially a sequence-to-sequence model. It's very similar to what you are doing if you were to do machine translation. For example, you have an input sentence, and you translate the sentence into another language. For example, you have an input sentence that is in English, and you want to translate it in Chinese. And you can treat it as two sequences because essentially a language, you can treat it as a sequence of words. And then if you treat it as a sequence of words, that's essentially a sequence. For example, a sentence of 5 words, that's essentially a sequence of length 5. Right? So that becomes a sequence learning problem. I'll be talking about this. And if there were more time, because I also do a little bit of a theory for recurrent neural networks, and there's a lot of we actually do not understand that much about how recurrent neural network works. So if there's more time, then we can talk about that for about recurrent neural networks and how what's our current understanding of recurrent networks and why it usually fails for time series predictions. Usually you can use simpler models for time series predictions, and that works almost as well as if you were to use some more complex models such as recurrent neural networks. Okay, so question generation for educational content. First of all, why are we doing this? And there are several reasons. Let me first skip all these slides to give you the most important slide here. So suppose there's an instructor teaching sociology, okay, and her name, say the professor's name is Alice, okay. If there's to a point that the instructor has to teach a huge class, for example, if the professor wants to put the class online, right, then the professor will have a couple of thousands, maybe tens of thousands of students to work with. And think about this: if the professor wants to assign the students homework assignments, right? One way you can do is to assign the same homework assignments to all of these questions. Same homework assignment to all the students. That's an option. The other option is you probably also want to do some personalization, which means that depending on the learning trajectory of each student, you want to assign the students different questions to better fit their learning trajectory. So here's a question of scale here, right? There are two questions here. One is that with this many students, given that you know the students, what is the learning state of each student, how would you select and assign the questions to each student? Right? For example, how would you give the students the questions among a question pool? That's one thing. Two is that if you were to write new questions, right? How would you? It's very labor intensive to write new questions, given that you have other things to do, and then there's that many questions. So there's actually a problem of scale here for two problems. One is, what if you want to do personalization, right? Giving different students different questions. And two is that what if you want to write new questions? And this is something why that we designed this, basically started this research program, is that we want some automatic ways to automatically generate questions from textbooks, right? So suppose there's some kind of a system sitting over there, right? And then you give the system two things. One is you give the system a textbook, right? In this case, the textbook is a sociology textbook. And then you also give the network the learning history of the students, right? And then the system automatically figures out what questions to give to each student. You want a system like this, then the professor will be very happy because now you have some automatic system to assist the professor to assign questions to students, and now the students is also happy because they get some personalized treatment, so that nobody's getting the same questions, and then you get things that fits your learning history and your learning trajectory. In in this work, we actually simplify the problem to ignore this part, because figuring out the learning history of students is by itself a really difficult problem. So in this work, we actually, the system's input is essentially just the textbook. And then we are trying to generate questions based on the text from the textbook. Okay, so that's the input-output relationship of the system that we want to design. Yeah, it's here. So the input is input text. It could be something like this. This is talking about deviance and social change. So, and then we also need a very important element as the input, which is where in the input sentence do you want to ask a question about? Because for a given sentence, you can ask many different questions. Right? For example, University of Houston is a university in Houston. Right? You can ask different things about this. You can ask which university is in Houston, and you can also ask where is the University of Houston. Right? So you can ask different questions depending on where you want to focus on in the sentence. So the input actually is the sentence plus where you want, like the selected words in the sentence that you want to generate a question on. In this case, if I want to ask a question about the last 3 words in a sentence, then my question would be something like this, right? If I want to ask about something else, for example, if I want to ask about the word deviance, then the question would be something totally different. So my input needs to, the system needs to know 2 pieces of the input. One is the sentence I want to generate a question on, and 2 is where in the sentence I want to generate a question. Okay. So given that, what's our criterion for an accepted question, right? There are many ways to say that what is a good question. For example, when you talk to a real instructor, the professor or the instructor will probably say, oh, I need my question to be of some educational value. For example, you probably want to help the question to help the students to improve their learning in some way or evaluate it in some way, right? In our case, we actually simplify the problem a bit, because evaluating the educational value of a question is not that is not very easily quantified. So we actually simplify it to just 2 criteria. One is that you need the question to be fluent, right? Meaning that it doesn't have any grammatical errors. 2 is that it's relevant. Relevant means that you're not asking some random question to give you your input, even though your question might be fluent. So you want your question to be both fluent and relevant. I think those are the 2 most basic criterion if you want to generate questions. Later, we can then think about how we can quantify the educational value of a question. But those are the 2 criteria we're focusing on in this particular work. Okay. So we designed this thing called the QGNet. It's a very dumb name. It's short for Question Generation Network. Okay. So basically, what it can do is that it generates fluent and relevant questions. And then you can do that given different input, like text from different input domains. For example, you can generate text from sociology. You can generate question from history and also biology. Those are the 3 textbooks we tested on. And then it adapts to text from the above 3 text domains. So I'll talk a bit about how this thing works. It's essentially on a very high level, and you'll see a bunch of cartoons leaking around here. It's essentially composed of 2 parts. So on the one hand, you have a machine reader. Okay, so the machine reader, what it does is that it's processing the input sentence, like a sentence or a paragraph from the textbook. Okay, so and then you also have a generator. The generator is essentially once you have read the input sentence, and then you want to generate the question. So that's what the generator is doing. It's generating the actual question. So here's a cartoon, and then the processing of the input is sequential. Okay, so for example, here we have the same sentence you've seen before. What the reader will do is that is looping from the first word to the last word sequentially over the input. So it's processing the sentence like this. Okay, and it's done. So basically, it's looping from it's processing from the first word to the last word sequentially. That's what the reader does. After that, you have some intermediate numerical representation of the text. Okay, remember the text is usually, I mean, the raw text is looks like a string to a computer. But then in order for the for a computational model to process it, you probably want to convert the string to some numerical value, right? In this case, each word is represented as a vector. Okay, and then the entire sentence is converted to some kind of intermediate representation. So you have some numerical value of your input, that then the generator will take this intermediate representation of the input to generate the output. And how the generator generates the output is that it's generating the question sentence word by word, okay, from the first word to the last word. So here's another cartoon that's illustrates how the output is generated. So first you have the word what, right? And after that you have word by word until the entire sequence looks like a question to you. And this framework is exactly what people use for machine translation. It's just that the input and output interpretation are different to us. The input and output interpretation for the machine is almost is very similar. They're just the numbers, right? So for example, if you use the same framework for machine translation, then your input is not a sentence from a textbook. The input could be a sentence in Chinese, right? It's a sequence of characters in Chinese, and then your output is, for example, if you do Chinese to English translation, your output is a sentence in a sequence of words in English. And then our interpretation for the input and output are different in that case than in this case. In machine translation, the interpretation for the input is a sentence in one language, and then the output is a sentence in another language, right? In our case, the interpretation for the input is a sentence from a textbook. It's a statement, or yes, some like a sentence in the textbook, and the output is a question that's asking about certain things in the input sequence.
So how do you select the foster social change? Is that a label, or you?
This thing is for in this work is labeled. That's a good question. So so you need the labels in order to generate questions. Otherwise, the system will just output the same question all the time. This is 2 years ago, somebody did the question generation on just a sequence. I mean, just a piece of text without the labels, and then the system will generate the same question all the time for one sentence. But you probably don't want that, right? I mean, for one sentence, depending on where you want to ask, you want to generate different questions. So later on, future research is going to focus on like selecting those labels automatically, right? Like figuring out the phrase or words of interest that you want to generate questions on, and then use those labels as input to the system. Currently, we need those labels to generate questions. So what we do now, because we don't have those labels in textbooks, what we do now is that we just do simple, what do you call it, like tokenization, and then use some like super simple heuristics to find the phrases. So actually, we over-generate the number of questions because we have lots of phrases for a particular sentence, and then basically we just select the ones that looks interesting. But of course, in the future, we want to automatically and using some good heuristics to select the phrases that we want to generate questions on.
I guess that would also come from the students' trajectories, right?
Yeah.
The phrases could come from where partially relevant for the student.
Yes. So one thing we're actually doing at OpenStax is that students have we just recently implemented a highlighting option for students. So basically, the students can highlight stuff on the textbook, right? And that means maybe we can just use those data for generating questions. And that's actually also useful for doing personalization because different students will highlight different things, right? And the things that each student will highlight is probably something important to them. So then we can generate questions using the students' data and then on the phrases that they highlighted. But that's not part of this research.
Jack, you mentioned which books, topics so far you practiced?
Yeah, so we covered, we selected sociology, history, and biology. The idea is that we select one textbook in three domains, right? So biology is in science, sociology is in social science, and the history is in humanities. So we want to select textbooks in diverse domains to see that it actually works for different domains.
Is there an extra step of coming up with different word embeddings and word direct kind of dictionaries?
Yeah, this is a good question. So for word embeddings, we don't train the word embedding. We use the pre-trained word embeddings for to train the system. We use global word embeddings. Okay, so this is the general framework. We actually also, so the reader and generator are LSTM networks. So LSTM networks are one comment because the previous talk, maybe the one before that is on recurrent neural networks. Recently, there's a newer model for doing text. It's called transformer. I'm not sure you guys have heard of that because so transformer is essentially feed-forward networks plus attention module. So it completely eliminates the recurrency in when you're doing sequence processing. And the reason you can do this is that for language is not just some a regular sequence processing because you know the length of the language beforehand. Right? When you do regular time series, you don't know how long the time series will is going to run. But in this case, you know exactly beforehand. I mean, although the length of the sentences can vary, but you know the lengths beforehand, and you can take advantage of that because eventually the intermediate representation, this thing, for the entire however long your input sequence is, for the intermediate representation, you want a fixed length. Okay, so that means you can somehow take advantage of knowing the sequence length beforehand, and also the fact that you want a fixed length intermediate representation. So if you want, if you do some clever algebra, you can actually completely eliminate the recurrence if you process sequences, if you know the length beforehand, and also if you want to convert the varying sequence length into a fixed length representation. And that actually works super well, and then that also led people to even claim that when you do text, you don't need to use like any recurrent structures at all. Basically, two things you need: one is the transformer, and two is attention. That's the claim. Nobody knows why, but it seems to be the trend. If you just if you want to do any kind of like text processing, you probably want to use transformer instead of any recurrent architecture in practice. Okay, that's my comment. But then this thing can be readily updated, right? You just replace this module by a transformer. That's it. And there are many implementations of transformer, and you can hopefully improve the performance. I haven't tried that, but the performance of the quality of the generated questions might be improved if you replace the two modules for the reader and generator to a transformer instead of a LSTM network. Okay, there are actually two more tricks here. We actually use the attention mechanism and the copy mechanism. The high-level explanation for these two modules is that the attention mechanism is basically when you do the generation for each word, right? You don't just look at all of the words in your input sequence equally. You actually pick, and this is automatically learned by the network, which one of the words in the input is more important than the others. And the attention model basically selectively focuses on the words that it thinks is important when it's doing generation. Okay. Copy mechanism is even more important here because what copy mechanism does is that, as the name suggests, it has the ability to directly copy words from the input to the output. This is very important because we want the question to be relevant. Right? Remember, one of the evaluation criteria is that we want the question to be relevant. And one way you can do this is that you probably want some of the words, right, in your question to your input to appear in the question, right? Like I mean, think about it when you ask a question about something, right? When you want to make the question to be very relevant to the input, there must be, or I should say, very often there must be some words that appear in the question that also appear in the input sentence. Right? And we use this copy mechanism to enforce this, to basically say that to train the model to select which word should also appear in the question. Okay, so that's what the copy mechanism does.
So how similar is to the GAN generator and the discriminator? Is there similar structure or there's no relationship here? For the image processing, there's a generated new image.
I think the training procedure is a little bit different. So you can treat this entire thing here as the generator in the GAN. So here we don't have the discriminator. So basically, the training criterion is by finding the finding the similarity between your generated output to the input. But the generated out, like how you measure similarity is different in this case than in GAN. In GAN is by using some probabilistic what do you call it, like some divergence criterion, and they can use Wasserstein or Carroll divergence in this case. In GAN, in this case, it's by measuring negative log likelihood. So the criterion you measure the difference is different in those two cases. Okay. Some citations. So I claim the model can generate questions that are fluent and relevant, and also it adapts to different text. And let me quickly go to some generated examples. I'll skip the experiments. Okay. Here's an input sentence, right from sociology. Okay. I'm not going to read it, but if you want to generate question on the word gender, right? Maybe you can think about like what question you came up with in your mind, and I'll show 3 different questions. By 2 of them are baselines. One of them is by the model I designed, and then maybe you can compare the question you came up with to these 3 questions I will show very soon. Okay, so this is a question that our network generates. Right, I would say it's a reasonable question. Okay, it's satisfied. I mean, obviously satisfied the 2 criteria. Right, it's fluent, is relevant. You can say something about whether it's actually valuable or not, but actually, at least it satisfied these 2 criteria. This is one of the baseline. The question outputs by one of the baselines. Right, and here's the. You'll notice that it's not very grammatical at the end of the sentence. And here is another sentence by a different baseline. Right? And you'll notice that this part is kind of strange. Right, so you have some qualitative like comparisons of the quality of the question generated by QGNet compared to 2 of the baselines. And I'll show you. Oh, also this word is like it doesn't appear in the original sentence. So it's you can say that it's not relevant. Okay. Here's another sentence from history. Okay, and let's say we want to ask about this, the Indian Removal Act. Right, here's the question that the network generates. Let's compare it to some of the baselines. Here's one of the baseline. When you read it, it looks like a good question. Yeah, unless you focus really on the beginning of a sentence, it doesn't appear to be super grammatical at the beginning of a sentence. Right. The second question by. Right, the last part of the sentence is not. I mean, this is so this is a recurrent. It's kind of a common problem for like deep learning based model, because you don't have guarantees about what the network actually outputs. So I think in practice or industry, you probably want to. You probably still want to use some heuristic based models, because that can give you. You know why your model doesn't perform well, and that's because your heuristic is not good. Maybe that's because your tokenization is not good. Maybe that's because you didn't select the phrases too well and things like that. In those models, you have no idea why this model will output like a weird sentence. In most cases, right? Like in most cases, I have this average evaluation, like a human evaluation, right? On average, the model actually performs well, right? So this is a bar plot showing the accuracy, showing the human evaluation, the human perception of the generated questions. The higher the bar, the better. And then on the highest bars are the evaluation results for our model, and the left two ones are for the baselines. So actually, you can see that the model generates questions that are on average is interesting and good enough. But the thing is, I think most people when they want to use this thing in practice, that it's very bad if you don't know why the model fails. You want to know something about how the model works, right? So that is easy to diagnose, and then maybe to later on, maybe you want to among the list of questions the model generates, you want to throw out maybe half of them, or maybe some portion of them that are not good. But then you don't have a very good evaluation criterion for how you would keep certain questions, how you don't keep certain questions. And then that's basically it. I mean, this is a model that can generate questions that are fluent and relevant. And the last thing I want to show here is the code is actually online. You can download and try it. Where is it? Okay, here. So the model is online. This morning I just fixed some bugs in the code. So it's very straightforward. There's a very good documentation. I spent some time on it. It's very straightforward to use. So I encourage you, if you're interested, you can download and try. And also this general framework, this sequence processing framework is very useful for. I mean, if you're doing something else, if you're doing translation and other kind of things, and then this repo can give you a good point to start. Okay, that's it. Thanks. I think I run over time. But.
Thank you. So maybe 2 questions?
No follow-up questions. So you talked about feedback from the students being part of the question making process. Did the questions become harder for certain students, or the students that fall behind just get more questions about that same material until
right? So this is something we actually didn't do for this project.
Okay.
And so if you look at this graph, right, we actually didn't take into student feedback into consideration when we are generating questions.
Okay.
So the only input that the model takes is the text.
Okay.
That's it. But it's when I was presenting this at the education conference, there are a lot of concerns because people say, oh, your network is not actually evaluated on the actual education value, and I agree, and that's very important. Otherwise, your generated questions don't have any education values. Then how useful is this? In this project, we make this entirely an engineering problem. Right? In the case that we don't take human feedback. But eventually, yes, we want to do something like that to select part of the questions that the model outputs and actually put them in production, in use, and then do some A/B testing, compare the students' performance if they were using those questions compared to the students when they use human-generated questions, and see how the performance compare. I think the eventual result, if the result is comparable, then that's good, because that shows that using machine-generated questions, you don't lose performance. You achieve comparable performance, and that's good. You don't necessarily need to have improved performance. Yeah. Yes.
What about text that's split up into multiple sentences? Would that be covered in the future?
Yes. So yes. This model, it takes one sentence up until 7 sentences, but the glitch here is that you have to train them separately. So if you want to train a model that takes 1 sentence, then you probably want to train it only on 1 sentences, because the longer the sequence makes it harder for the model to process. You could also so it doesn't. So what I'm saying is that you can't take like even if the model is trained on one sentence, you can still process 7 sentences. But the performance for this model, if you were to use it on one sentence, will be better than if you were to use it on 7 sentences. Yeah. So if you wanted to use longer sentences, you probably want to train it also on longer sentences. For example, like a paragraph instead of a sentence. Yeah. Okay. Thanks.
Thank you. Our last speaker and the most important one from Zhenzhen Zhou. So she graduated from Virginia Tech and specialized in industrial engineering. She's currently a data science consultant in oil and gas industry. And she has many expertise in many domains, including digital signal processing and statistics and chemistry, etc. So welcome, Zhenzhen.上面能看好像啊，上面能看出，好像就第一个是难，后面都好了是吧？那无所谓了，那就这样。就第一个是这样。
Hi everyone. My name is Zhenzhen. I'm a data scientist from Accenture. So I'm very happy to share the story I had with a list of friends here, and they all come from oil and gas industry. They are very excited about deep learning. The topic today is the deep learning approach in characterizing the saw bodies in seismic images. So I will first give some background in the seismic images and also recap on the CNN, and then go through our workflow of internal data preparation, model fitting, and post-migration, post-QC, and then finally give the conclusion. So seismic industry is a very traditional area in the upstream. In this figure, it shows how the acquisition survey is done. Thousands of recording sensors and a few L gun is hooked to the survey ship. So the survey ship is moving, and the L gun continues to create and generate the sound energies. The sound waves bounce back from the rock formations, and they are recorded by the sensors. The recorded sensors then transduce these ones to digital signals, which will be finally processed into the images on the right side. So the seismic exploration is just to give a view of the subsurface images. So the geologists can, based on the seismic images, to explore the fluid or gas contents. The saw boundary interpretation is very important for understanding the geostructures, and they are very critical for the hydrocarbon explorations. The saw boundaries usually very bright events, and they are coherent, so it's very easy to be visualized. A lot of the seismic interpreters usually spend a lot of time just doing hands-on picking to pick the saw boundaries. And this was what I was done 2 years ago. I just keep picking the horizons on a 3D seismic wall, and I still remember the pain I had on my wrists and eyes because of picking this day by day. So fortunately, because most of the top saw and basal saw, they are continuous and they are bright events, so someone developed a smarter way. Users just need to pick several Cs on the continuous events. So the rest of the job is done by computer, by calculating the correlation within a small window. So the auto tracking here, you see the different color stands for different depths, but it's very easy to break down when the top of saw and basal saw is not that coherent. We all know that human evolution becomes super fast after the visions developed. So, so when computer vision meets seismic images, will there be any kind of sparks? Like, will the deep learning catch the intelligence of geologists and be able to analyze the soil geometry? And this is what actually we were doing like months ago, when TGS actually operational headquartered in Houston, launched a competition on the Kaggle platform and released 20,000 subsurface images. These images, they are chosen at various Gulf of Mexico locations. We got 4,000 training images, 18,000 blind test images, which is a quite big amount compared to the training we have. And each image is 101 by 101 pixel. And each pixel of training images is labeled as either salt or sediment. The example here shows the images and the salt masks. So each pixel is identified as salt or sediment, and I will call this as salt mask. So what we need to do is, on the 18,000 images, we predict the salt masks. Also, the depth information is provided. The recap of the convolutional neural network. I know a lot of you already are expert on this. So the common use of convolutional neural network is for classification or object detection. And the image here, in the first, the machine doesn't know whether it's a truck, a horse, or a car. Then the features are extracted into hierarchical information by the CNN. The architecture here allows the network to concentrate on low-level features in the first hidden layers, and then on some of them into high-level features in the next hidden layer, and so on. So, in other words, the low-layer features are something like edges and high frequencies, and the high-level features, they are more like object face recognition, geometry shape. The pooling layer here is just to shrink the image to reduce the load and limiting the overfitting. Computing and accuracy is very straightforward for binary classification. But here, this is the image segmentation problem. In this kind of competition, the metrics used to evaluate the segmentation map is intersection over union, the IOU score. To calculate the IOU score, we need to know what is the ground truth label of the salt area and where are the predicted salt areas. I have included a visual example here. The red box here is the predicted bounding box, and the green box here is the ground truth bounding box. The IOU is calculated by the area of overlap divided by the area of union, and the last figure there gives a sense of what kind of value is corresponding to poor or excellent prediction. So we have 4,000 images. We have 18,000 test images. Is there any way that we can have more data if we don't have more data? The simple answer is minor alterations. The minor alterations including flip, like horizontal flip, vertical flip, or scale, crop, adding Gaussian noises. And it's often better to generate the training instance on the fly during the training. So what we implemented here is a test time augmentation, which is during the trainings, augmenting the training images batches by batches. How are the data augmented is based on the random generator. For example, we flip a coin and decide, okay, now we flip this image, or we add a noise to this image. These are the examples of the augmented images for training. The top row shows the original images overlay with the salt masks, and the green shades here are salt. The rest of them are horizontal flipped data and the shear rotation data, or the combination of them. One thing we need to pay attention is that any kind of data augmentation is better to make geological sense, because salt is never above seawater bottom and also away beneath the shallow structures. So we never use the vertical flip. And also, if a shear rotation angle is too big, it will destroy the wavelet on these salt boundaries. And some other pre-processing we tested, image normalization based on adjusting the amplitude histograms and make the distribution equal. This help boost some weak events and balance the amplitude. Some brightness corrections with nonlinear operations, age detection with the gradient calculating, vessel shape detection, which usually detects the tube structure or container structure, and the binary images for help identifying the boundaries. Conventional CNN is a great choice for binary classification. In terms of image segmentation, a very popular method is using the UNet. UNet is a very elegant network. As displayed here, it's U-shaped and it's symmetric. The left side shows the contracting branches, and the right side shows the expansive passes. So the left side includes a lot of convolutional blocks, which keep downsizing the input into different features. While the right side, it's a lot of transpose convolution blocks that keeps upsizing the features. So the convolutional blocks, they are composed of basic convolutional filters, batch normalization, ReLU activations. The right side two figures shows examples how convolution can shrink the samples and transpose convolution upsamplings. And one thing I want to mention is transpose convolution is also known as deconvolution, and why transpose convolution is preferred over just interpolation of the upsampling. Because interpolation upsampling is something like manual feature engineering. So there's nothing new the network can learn about. But transpose convolution, it contains a lot of learnable parameters. So it's very good for the network to learn by themselves. The gray arrow here stands for the concatenation connector, which helps propagate the location feature maps generated during downsampling into the global information while upsampling. This is the highlight of the UNet. So it never loses the downsampling location information from the left branches, and which is very helpful to generate the last prediction map. And the left side, right side are connected by the bottleneck, which are very simple convolution blocks. So inspired by the UNet, we added a little bit of superpower to it. So the ResNet origins from the thought that performance of deeper networks should always perform better or at least equal to the shallow network. But in the real world, this is not the case because of vanishing gradient problem. So someone think, okay, maybe it will be helpful for the output layer, for the high-level layers to learn directly from the low-level layers. And this is the most basic res blocks example. Okay, here's the mouse. That's not mouse. So the input here is X, and this is a convolutional filter, batch normalization, and the random activation. This operation is called fx. So the output here, hx equals to x plus fx. So eventually, what the output layer learns is the residuals between input and output. That's why it's called residual block. When the input dimension is the same as the output dimension, it can be directly connected. That's called identity block. When they're not equal, when the size they're not equal, for example, x is 9 by 9, output is 3 by 3, then we need to add a convolutional filter to reshape the input and bring down to the same size as the output. That is called a convolutional res block. The lower images here shows the structure of ResNet 34. So you can see it's composed by a lot of residue blocks. Like the curvy arrows here are the same as the direct connection, and then several convolutional filters. And here shows different number of filters. And convolutional filters, we know that's downsizing. But if we replace the convolutional filters to transpose convolutional blocks, then it can do upsampling. That's why ResNet is very ideal to be used as a UNet backbone, because it can be used as either contracting paths or expansive paths. Eventually, our model just the combination of two ResNet connected by simple blocks of bottleneck convolutional blocks. We started training this model with pre-trained ResNet weight, and this is very helpful and greatly speed up the training process. The loss functions. Binary cross entropy or log loss is ideal for classification problem. Dice loss is calculated as the grounding truth error multiplied with the prediction error and divided by the sum of them. These two, they are not directly related to our final IOU score. So we use them for the first pass training. The lowest loss, which is similar to computing the gradient, which is iteratively computing the gradient of the 1 minus IOU score. This is directly related to IOU. So we use it to fine tune our second pass model fitting. And some other highlights from our work that I would just quickly go through it, because it's not really complex as it looks like. So usually network weights each of the convolutional filter in different channels just give the equal weight. So what is done here is just giving different convolutional filters different weights, like pay different attention. This is different weights are calculated by the feature maps and some global average value and then activation function. And the hypercolon usage. So a hypercolon at 1 pixel is a vector of the activations of all units that lies above that pixel. The idea is just instead of using, for current layer training, instead of using the features coming from the last layer and the previous last layer, and then the hypercolon is using all the features from all the previous layers and combining them to current training. That's so never lose any features during the training process. Okay, this shows our training process monitored by the tensor board. The top row here is the training dataset accuracy, loss, and IOU score. And the bottom row shows the validation dataset accuracy, loss, and IOU metrics. With data augmentation, eventually we have 8,000 images. So the ratio, the training validation split is 0.8. So the training data is 64,000, and then validation data is validation and data set is 1,600. And you can see here, after some point, the IOU score stops increasing, and then the loss actually got increasing. So some best model parameters is between these points. We also did some interesting tests about cyclic learning rate. The benefit of cyclic learning rate is within a few iterations, you can use a various range of learning rate instead of just simply decay. There are different approaches of cyclic learning rate schedule, but the most important thing is cyclic learning rate can help get off the local minimum multiple times. Finally, the example of predictions on test images. These are 40 examples out of 18,000 test images. So not bad, huh? Pretty good, actually. Maybe it's a few pixels here that's missing, but most things are very good. Jigsaw puzzle. Now the last question bothers us is, should we do the quality control of the 18,000 images one by one? That's too difficult. So instead of doing that, we calculate the similarity score for each images at the 4 boundaries. And based on the similarity score, we eventually moved and connected the 18,000 images into 200 to 300 big patches. This is a bigger picture how the subsurface looks like, and each one has an image name on top of it. This is helpful to speed up the QC and our iteratively improvement. So all of them, they have a similarity score in the neighboring boundaries. So many tests we have done. That's a lot of efforts. We have modified ResNet. We have added new text, different data augmentations. In the last 2 weeks, we did a cross-validation and on some of the 5 files. These are some test scores. Actually, our best score is about best IOU score is about 0.86, so close to 97% of accuracy of prediction. Conclusion. So take-home message: we integrate ResNet and UNet to solve image segmentation problems. The architecture is dedicated to restoring the pixel location during the downsize pass, and then pass it to the upsizing passes. With the help of computer and deep learning, the image interpreters, they may start looking forward to spend time doing other interesting things instead of just picking horizons all day. We also have a lot of data. We also have a lot of lessons learned. So future work. I just want to highlight one thing: semi-supervised deep learning. So why semi-supervised learning is a very good use case here? Because we have 18,000 test images. That's a great amount of information that we couldn't have any way to incorporate in the model fitting. So once we have the initial, very good initial model, we can predict the sort max on the test images and use it as pseudo-label data, then combine them to the training images for further iteratively training. This is how the pseudo-label data they are used. It's like keep softening the decision boundaries. But the assumption here must be both training set and test set, they must follow the same distribution. Okay, I think that's it. Thanks for all our team members for the great effort and excellent teamwork. So our score is at top 7 of the 3,000 teams. And thanks to Yuan for organizing the workshop. And thanks for, we ran a lot of GPU tests using Google Cloud platform. Thank you.
Questions?
I just want to go. I'm hungry. Okay. Yeah.
I really like the jigsaw approach.
Yeah.
As a sharp little thing to do. Now, were you just doing it 2 edges at a time, or did you ever use multiple edges to help make sure that it was locking into the right place? Did things normally line up just on one edge? Was that normally all you needed, or did you sometimes?
So the similarities. Yeah, good question. So the similarity scores are calculated on every edges. So every edge has, so for one image, every other images are computed similarities on the right side and top side, left side, and then the bottom side. And the similarity score are ordered in some way. So eventually how these images are connected is based on the ordering of the.
But there was no rotation. You only correlated tops to bottoms. Not tops to tops.
What do you mean by?
Right. Well, you mentioned earlier that when you're doing augmentation that you didn't do any vertical flipping.
Oh no,
so
just
I presume you
yeah.
Which way it was up. So to draw some, make sure to only compare left side to right side and compare top side to bottom side.
Yeah. So the data augmentation is only used to help for the training process, so we can have more data. But we didn't use it here for
But it was a hint that you knew which way was up.
No, we didn't flip the vertically. Yeah, we only did horizontal flip. And the connection, the patches here, we don't have any of the augmented images. It's all the true training images.
So you take the step of only comparing tops to bottoms, and only comparing left to right, or you just compare them all to each other?
Compare them all to each other.
Can you explain on this image to get better result?
So that's another question we thought about, but because the data self, it has some problem when it's prepared for the calc computation. So you can see some of holes. Like ideally, this is the top salt, so this is the base of salt. But for salt flood, for the first iteration picking salt, all the images still need to be solved. But because of normalization, eventually the mask becomes 0. So that's not a very good way to be used. That's not a very accurate way to be used as additional training.
I have a question about your pseudo labels. Are you saying that pseudo label there are noisy data, or there's data that's already predicted by the model?
Yeah, the pseudo data is actually the prediction of the test data.
They might be not correct, right?
They might be not correct, yes. So yeah, the initial model must be very good.
And another thing is that since at the beginning you mentioned that it's 3-dimensional data, but are you actually training them with the information of the depths, or does it look like you only train them with the 2-dimensional information?
Yeah, the depth information is one constant for each image, so we didn't use it in the training set. Yeah, we didn't use it as additional features.
So actually, since I'm working in a biological large-scale image, we have like similar question about the 3-dimensional data. We're thinking about adding additional information of the previous and the layer information of the adjacent channels and make it manually format an RGB image, and then it kind of using information of the depths.
We tried to use depths here. We tried to use we also tried to use the accumulated samples from top to bottom and add in the depth information, but it didn't help us improve the score. So yeah, eventually we didn't use it.
Yeah, but I feel it's key that if we, the depth information there might be useful that provide some additional information to help us today, because like the previous and the later channel, they must have share a big similarity with the later channel, right?
Yeah, that's true. But the case is here, it doesn't help. Yeah. I think maybe a better way is to have, for each, we have another dimension of images. Like we have images, we have some masks, we have depth for every pixels. That will be more accurate information to use.
Yeah, for this data set, the depth is not correct because for adjacent in the jigsaw puzzle, adjacent images, they have totally different depths. So the information of the depth is not correct. You mentioned about finally answer about why they don't find the right depth.
Any other questions?
Thanks to speaker again. Okay, at the end of this workshop, sorry it lasts more than 20 minutes than scheduled. And thank you all for coming, and happy Thanksgiving to you all.